Basically, we are here together to start practicing or to solve some practice exercises related to Finite Automaton. But I would like to start with reminding you what are we talking about. So let me share the screen and okay, polling. Okay. So basically, I would like to remind you that we are talking about a new model, computational model. The next lecture, I will compare it to have a non-finite, we have a finite.
Rina, you cut off every once in a while. You just were off for like 10 seconds. Not bad
So
now,
please,
but
okay.
yeah.
If usually my computer writes me poor connection, so if you have some problems with my sound, please tell me. I will go backwards and redo what I was talking about once again. So it's okay. Please tell me if you don't hear me. So basically, I would like to remind you formal definition of finite automaton. Finite automaton that we are talking about is 5 tuple. We have a finite set, a non-empty set of states. At least in a set Q of states, we will have at least one state. We have a finite alphabet. It can be binary alphabet 0, 1. It can be alphabet of letters ABC. It can be alphabet of the whole words, for example, red, blue, yellow, and so on. But usually we are using finite alphabet with single letters in it. Using
You
transition
again cut.
function. Okay, we are using transition function, and basically transition function is we have a current state Q that we are now, an input letter. We are moving from current state with input letter to the next state. So the transition function called delta. So we have some state Qi. We have an input letter sigma j, and we are moving from Qi and sigma j to the new resulting state Qk in this drawing. Okay, the next what we have, we have to define the starting state. It should be the state that we have an arrow entering it, and we have a finite state set. Finite set states can be actually an empty set, and also finite states called accepting states. The automat we built is deterministic. So for each states and for each letter of the alphabet, we want to have one and only one transition. So basically, let's look at this example, just a brief remind. So here we have an automaton with 3 states. So the Q is Q1, Q2, Q3. The alphabet here is 0, 1. The starting state is Q1. How do I know that Q1 is the starting set? We have an error entering it. So basically, if sometimes you don't know which state is the starting state, you just have to look at your drawing, to your state diagram, and find the state with the error entering it. This way, you know that it's the starting state. So in our example, QS is Q1 in this automaton. The finite state we mark with double circles. So in this automaton, Q2 is an accepting finite state. And the transition function can be defined by a table. So let's look. So we have a current state. Let's take Q1 as an example. An input letter. Let's take 0. Q1 0, I can see in this automaton that I state in Q1. So here I can find the resulting state. Q1 and 1 I move to Q2. So basically, once again, transition function delta gives us gives us an explanation where we should move. So we have a current state, an input letter, and we should move to some directions. Any questions? If not, I will move to what actually we are together. I will share the screen once again. Wait a moment. Stop sharing. And I will go to the set of exercises that we should solve together today. Wait, why I don't see it? Here. Wait, here. Do you see the exercises that we should solve?
No.
No? Wait, I will stop sharing and do once again. I have my tablet connected, so let's see. Now? Yes, now you see it. So
Yes.
basically the idea today is to solve all questions that actually practice questions in the lecture or after the lecture. So you watched the lecture, you know, at least you understand what are we talking about. And the idea is to solve the questions. I prepared the list of questions. I published it before the practice exercise. So basically we are starting now with the first question. You need to draw or to build a deterministic finite automaton for the following languages. So let's start with the first language. The first language, we have W over alphabet 01. The W contains substring 110. I would like you to take a time, 1-2 minutes. I would like you to draw the automaton, and then I will draw the solution together with you. If someone wants to help me, you are welcome. So basically, we will do it together. So we are starting with one language that accepts all words that contain substring
Rina, I don't know if you can hear this, but you're cut off for like 2 minutes.
לפתור את התרגיל?
כן, אמרה לפתור את התרגיל. רק אני כאילו איבדתי אותה, או שזה כולם פה?
לא, לא, כולם, אני שואל, אולי
כולם.
נפתור ביחד את התרגיל?
אפשר. תתחילו בכל מקרה, זה מה שהיא אמרה, כאילו. זה מה שהיא כיוונה עליו.
שמתי, עשינו את זה באחד השיעורים הראשונים גם של דיגיטל, משהו בסגנון. אני זוכר נכון.
עשינו את זה אוטומטה? עשינו את זה בסגנון אוטומטה? ציירנו ריבועי עיגולים?
עשינו את זה עם ה-Moore State Machine.
אז זה אותו דבר, בסדר, תעשו את זה. תרגול טוב. האמת עשיתי את זה כשראיתי את ההרצאה. רינה? לא שומעים אותך, את על מיוט, את על מיוט.
Okay, I switched to mobile network because I don't know, I have some problems with internet connection. Hopefully it will be okay. I will start sharing a screen whiteboard. I think you already solved probably the question. Wait, I'm reconnected here also. Share, let's see. Yes, okay. So, did you solve the question until you had connection problems? Okay, so basically we want to write a language or an accept to a language W. The W has some prefix, substring 110, some suffix, and that we know that W, U, and V and here belong to sigma star. So basically here is the definition of our language. If I need to give a formal definition, then I would like to tell that I would like to accept all words with substring 110 inside. So basically, if I want to build an automaton, that's what I will do. I will start with some state Q0, and I will mark it as an starting point with arrow entering it. And now basically the idea that I will start with the most important thing for me, accepting the substring 1, 1, and I go to Q2 and 0. If I manage to find 1 by 0, I know that I should move to, sorry, I know that I should draw an accepting state. So basically, now I have the main part of the automaton, that I can see that my automaton accepts 1 by 0. The problem with my automaton that it's not deterministic. Deterministic automaton for each input letter and for each state should give me an answer. So someone wants to help me to finish this automaton? What I should do with Q0 and 0?
Yeah, first add the state 0 to Q0. That if you get 0, you repeat itself, yeah.
Okay.
Now
Q1
do the
and 0?
Q1 and 0. 0 go to the start. To Q0.
Because it cancelled that we already saw the prefix 1. Okay.
Right, cancel 1.
And Q2, 1.
If you get 1, then get 1 back to Q1 because you have no,
not Q1.
Right.
Exactly. We should stay here because if we move to Q1, actually I've got the same answer also yesterday. So let's see, if I go to Q1, to return to Q2, I need additional ones. So I now have a loop of even number of ones. So for example, if I would draw the error from Q2 to Q1, then the word 1, 1, 1, 0, 1, 1, 1, 0 won't be accepted because on the first one, I will move from QFS to Q1. The second one from QFS to Q2. The third one, I would move from Q2 to Q1. And it will be a problem because now I have the 0 and I go to Q0 instead of moving to Q3. So basically, when I get 1, I should stay in Q2 because it means that I still continue with the prefix 1, 1, with the prefix of 2 ones. And now Q3, if I get any suffix, what should I do after I saw 110?
Just repeat 0 and 1 because you did it.
Exactly. We stay here with 0 and 1. Any questions? So basically, you start with the main part, the substring 110, and then you complete the automaton to be the deterministic finite automaton. Okay, so we move to the next question.
Could we have also did it with 2 states?
No. Here you can't. This one is the minimal finite state automaton. By the way, we didn't talk about minimal finite state automaton. In homework 2 and the next homework 3, you will be asked to build the minimal automaton, but we will define what is minimal automaton only in 2 weeks' time. So basically now when you try to solve the problem, you need to draw, at least try to draw the minimal automaton, but here minimal automaton has 4 states.
But if I would have said that I have, let's say, Q0 and Q1, and each for the letter 0 of Q0, it goes to Q0 as you did here, or it goes to Q1, and then in the state of Q1, if we have 1, then it goes to itself, and if we have 0, then it goes back to Q0.
1 stays here,
and 0 goes back.
No, so let's see. Let's try the word that I used. With your automaton, I have 1, additional 1, and with 0, I return to QFS. So if you here will stay with 1, you have to move with 0 back to Q0. So basically, you have 3 meanings. This one tells you prefix 1. This one tells you prefix 1. This one, that's why it's a final prefix or substring 110. So you need here, since you are watching 3 letters, you need to have at least 3 arrows. To have 3 arrows, you have to draw 4 states here in this example.
Okay, thank you.
Okay, the next question, wait, I will stop sharing screen here and I will start sharing once again the questions. So we are moving to the question number 2. Actually, it's the same question as number 1, but now I'm looking at complement of previous language. So now I would like to accept all words W that does not contain substring 110. So once again, what I'm looking is, I would like to find 110. And if I found 110, now I would like not to accept the word. So
can we just replace accepting states and rejecting states?
Exactly, that's what I will do in a moment. Yes. So basically, you gave the answer. I wanted you to think about it a little bit. But basically, sometimes the whole idea of this exercise that sometimes it is easier for us to solve a complement question. So basically, I am talking about language L that accepts W. The W is not containing substring 110. So W is not having some prefix, substring 110, and some suffix. And U, V, and W belong to sigma Kohovit. Also, I could write the following definition. I could take sigma star and I could write minus with previous language, let's call it L1. So the same definition can be given. So sometimes it's difficult to explain or to give the full formal definition of what we are looking for. Sometimes it's much easier for us to give the definition of the complement language. So if I have an easy definition of the complement language, then I can write something like I did here. I can write sigma star minus complement language, and I have a formal definition of what I wanted. So once again, a brief explanation. We start with Q0, and we are watching, or we are trying to find the substring 110. And if we have 110, then this state is not accepting. All the rest of the states we have here are accepting states. So Q0, 0, we stay in this state. Q1, 0, we return back because we actually canceled the prefix of substring 111. When we have 1 in Q2, we stay in Q2. And after finding substring 111, when we move to Q3, we should stay here with any input letters. So basically, the automaton is the same automaton that we had in previous example. The only difference that all accepting states are now rejecting states, and all rejecting states are now accepting states. Any questions? If not, good. We continue to the third example. So once again, I would like you to take a minute and to try to solve this question by yourself, and then we will do it together. So here we have a language, once again, over alphabet 01 of all words W, such that W contains substring 00 and does not contain substring 11. So basically the idea is that you have to watch two things. You have to find 00, and if you found it, good. You have to watch substring 11, and if you found it, once again, it's good because you know that you have to reject the word, and you have to watch everything in between. So please take your time. This automaton is a little bit more complicated than previous one, but the idea is to combine what we did in first language and what we did with the second language, and to build the automaton that actually watches or tries to accept substring 00 and tries to reject substring 11.
What's the minimal number of states we can do this at?
I think it's 6. Someone wants to help me?
Yeah, sure.
Okay, let's start for watching for 0, 0 substring.
Okay. So
So
you want to go? Go ahead.
Q0,
Yeah, okay. To some state with yeah, Q1. And from that, create to another zero, yeah, called Q2. And that's an accepting state, right?
exactly.
And from it, you can take an
From
arrow.
it, wait.
Okay.
From it, we
Okay.
will,
Okay.
let's start with not finding substring 1, 1.
Okay,
So
so
from
again with
Q0
1. Yeah. 1
with
to
1,
1, right?
I move to the next, I call it Q3,
Then another one, right?
Q4,
Okay, from
and
Q4, yeah, okay.
in
Go ahead.
Q4, if we manage to reach Q4, if we saw substring 1, 1, 1, does it interest us what we have next?
No.
no, we reject it
No.
anyway.
Rejected. So this state that I have to stay in it without moving, called the trap state, because I will stay here forever and it's a rejecting state. So basically, we currently finished the major idea of our automaton. If we have 0, 0, we accept the word. If we don't have, if we have 1, 1, we reject the word. Now we need to build deterministic automaton. Deterministic automaton means that for each input letter, we have a transition function. For each state and each input letter, we have a definition. So let's look. Q0, we have 0 and 1. Here we don't have any problem. We have the definition. Q1, we have a problem. We have only the transition with 0. So Q1, 1, where should I move?
Q3,
To Q3, exactly. Why Q3?
because you start a new substring with 1.
Exactly. I canceled the substring 0, 0, and I saw the first one that can be the continuation of the substring of 1, 1. So now Q1, we finished it. We have 1 and 0 transition. Let's talk about Q2. If in Q2 I get zeros, what should I
You
do?
stay in Q2. You stay in Q2.
Okay, I still continue to accept the word. If I have 1,
You need to go to new state, accepting state,
exactly.
Q4.
Okay, exactly. Let's see, I have an additional state, Q5. It's still an accepting state because we saw substring 0, 0, but we already started 1. Yesterday, some students moved from Q2 to Q3. It's a mistake, not because the idea, yes, you started to watch or to see or to find the substring 1, 1. The problem with Q3 is that it is not accepting state. And when I'm at Q2 and I saw 1, I still accepted substring 0, 0. So I should continue with an accepting state. So Q2 with 1, we move to the new state, Q5. Okay, I continue to Q3. Q3, I have a transition with 1. If I get 0, where should I go?
Q1.
Exactly. With 0, I cancel that I started to see, to watch substring 1, 1. And I started to watch substring 0, 0. Q4, we already finished because we know if we saw 1, 1, we're now at the trap state. We can't continue anymore. So let's finish Q5. If in Q5 I get 0,
You stay in Q5.
I stay at Q5. And if I get 1,
You go to Q4.
exactly. Any questions? So once again, if you have 2 conditions or 3 conditions, you basically start with Q0 and you write or you draw your conditions in the automaton. The main idea here was to find some substring 00 and to find a substring, let's say 11. If I found 11, I went to the trap state. If I found 00, I still had to continue, because if I found 11 once again, I once again moved to the trap state.
Wait, I have a question. Q5, when you get 0, it shouldn't return to Q2?
No,
you
because
don't have...
no, Q5, you told to you, sorry, Q5.
Yeah, because you have a 1.
No,
and
but yes, sorry.
right?
Yes, right. Yes. Sorry, we move with 0 here because we have to watch 1 once again. Because if I stay, wait, if I stay with drawing with 0 here, then the next one is not continuation of it can be not a continuation of substring 1. So yes, with 0 we move back to Q2. And it means that we saw substring 00. Why we saw? Because we saw it previously. That if I have the single 0, it doesn't matter, because once again I already saw substring 00, and I continue with zeros in Q2, and once again 2 1s move me from Q2 to Q5 accepting state, and from Q5 to Q4 rejecting state with additional 1. Thank you for the question, because I think I missed it. Okay. I will publish all the results at the end of the lecture and at the end of the second Hebrew group. I will publish also Zoom meeting if you want. If you don't want Zoom meeting to be published, I will only publish the solution of the exercises. Okay, last question that we should draw in automaton. We are moved to alphabet that has 3 letters, 0, 1, and 2. And we want to accept all words over alphabet 0, 1, 2. That's the word W is divisible by 3. Before you start solving this question, I would like to ask you the question about decimal alphabet. If I have a word that is written over decimal alphabet, how do I know that the word is divisible by 10?
It ends with a 0.
Ends with a 0. So basically, if you think it over, here we have the same question. We have alphabet 0, 1, 2. The question is when your word is divisible by 3. So when your word is divisible by 3. Exactly, the same idea. So once again, take a moment, solve this question. And we will do it in a moment together.
Rina, the alphabet should be with the star, no?
What?
W in the alphabet, in the question? W?
Should be a star, 0, 1, 2 star, yes. Okay. Do we accept an empty word or not? It's an open question.
Yes.
The question, an empty word, epsilon, does it have any representation? Does it end with 0? So basically, we had a whole discussion about it yesterday. Two solutions can be given to this question. We will start with the solution that empty word also belongs to this language. But basically, it's the whole problem with division. Can we divide an empty word? Is it divisible by 3? It depends. So basically, what I mentioned yesterday to the Hebrew group, and I would like to mention it also here, if sometimes you have some problems with the definitions that we gave you, the idea is please use the forum of the course and ask this question. For example, here, the perfect question would be, what do we do with an empty word? Should we accept it or not? So I will give you two solutions. We will start with empty word actually belonging to the language. So if an empty word belongs to our language, then Q0 should be an accepting state. What do I do now? If I get 1 or 2, I move to rejecting state. If I continue to get 1 or 2, I'm still in rejecting state. And when I get 0, I move to Q0. And if I continue with zeros, I stay here. Because we told to ourselves, if the number over alphabet 1, 2, 3 is over alphabet 0, 1, 2 is divisible by 3, it should end with 0. So now when we have a 0 ending, the word is accepting because we finished reading the word in Q0 and accepting state. Take additional moment and try to solve this problem when... Is everything okay? Please try to solve the same question with with an empty word not belonging to our language. Here we had epsilon that belongs to our language. Now I would like the solution without epsilon.
So we need to add another state.
Think it over if I need another state or I don't need another state. Q0 is definitely not an accepting state anymore.
You can switch Q1 and Q0 in the place and just switch arrows.
Okay. So if Q0, if I get 0, what do I do?
You go to Q1 and accept it.
Q1 and it's an accepting state. If in Q0 I get 1 or 2,
You stay in Q0.
I stay in Q0. If in Q1 I continue to get zeros, I stay in Q1 because I still have the suffix of 0. And if in Q1 I get 1 or 2, I continue to Q0. So basically, once again, we have only two states because we need to find out only if the word ends with 0 or doesn't end with 0. So if we have the word ending with 0, we accept it. The only question, what do we do with empty word? So if an empty word belongs to the language, then Q0 is an accepting state, and we did it here. And if an empty word epsilon doesn't belong to our language, then the solution can be found here, the second model.
The second model, there is also the question, what if the word have only zeros? Is it a number? It can be divisible or not?
Yes, only zeros. Actually, it's the same. Only zeros. It is divisible by 3 in this model because only zeros, we have the same problem here. So let's say that leading zeros is not a problem from our point of view here. Because we can't, if we get a string, the whole string with zeros only, we should accept it here for this language. So from mathematics point of view, we have zeros at the beginning that actually meaningless. But from Automata point of view, the zeros in the beginning may represent something. So the word with zeros, with leading zeros, from our point of view, it's a legal word and we should accept it. Any questions?
Yes, can you please go over it again?
What I told or what we did?
Can you go over the first one and the difference between them?
Okay. The first one here, the idea was that an empty word that doesn't have any letters in it, we decided that it belongs to our language, that it is divisible by 3. So if an empty word belongs to our language, that means that Q0 will be the accepting state. Then if I have additional zeros, I stay in Q0s because now I have the words ending with 0. If I have 1 or 2 and the word will be finished, I move to Q1 rejecting state, and I stay here with 1 and 2. When I get a new 0, I move to Q0. If I finish reading the word, I accept the word because I'm currently in Q0 state. But if I get additional input letters, I continue to move from Q0 to Q1 accordingly. And the whole idea, when I finish, where I will be. If I finish reading in Q0, then the word belongs to the language of the automaton. If I finish reading the word in Q1, then the word does not belong to the language of the automaton.
Why does it ending with 0 make it like an accepting state?
Because once again, I ask you with decimal alphabet. How do I know in mathematics that something is divisible by 10? I know that the number is divisible by 10 if it ends with 0. So here we had alphabet sigma 0, 1, 2. We had 3 letters in the alphabet. And the question was divisible, okay, modulo 3, divisible by 3. So I know that if something is divisible by 3, it ends with 0. So that's why when I saw 0, I knew that I have to go to an accepting state. The second model, we decided that an epsilon we don't want to accept. So if I don't want to accept epsilon, Q0 can't be an accepting state. So Q0 now is in a rejecting state. So if I get an empty word, I reject it. But once again, each word that ends with 0 should move me to an accepting state. So now Q0, with 0, I move to Q1, an accepting state. And until I get zeros, I'm staying here. If I get 1 or 2, I move to Q0, because if the word ends with 1 or 2, it should be rejected. Until I continue to get 1 and 2 in the input, I still continue to stay here in Q0 rejecting state. When I get additional 0, I move to Q1 and accepting state. So basically we have, once again, only 2 states. We have only 2 possibilities. Does the word end with 0 or does not end with 0? But now we have different solutions, because in first case, epsilon was a legal word, we should accept it. In second case, epsilon was not a legal word. Is it clear? Any questions? Okay, if we finished with this one, now we move to the next question that we had, and wait, this is solutions. I will publish it to you later. Okay. Now we have this task. Okay, this task is a class exercise. Here we are asked to give a formal proof that the language of the automaton and the language that was given is the same language. Once again, we were given the language L that accepts all words with even number of ones. This language we were given. This is our given language. The first mission or the first task was to build the automaton that accepts this language. The second step was to give a formal proof that the language that we had and the language of the automaton that we built is the same language. And now we will have a relatively long proof. I will publish my slides. And if you want, you can write until I explain the task. But basically, I would like you to listen and maybe to ask questions if you have any questions. But to see how do we do the formal proof, because I only do the first direction here. The second direction you do in your homework, in homework number 2. Additional thing I wanted to mention about home assignment, someone mentioned yesterday, actually not someone, I've mentioned yesterday that the date of the submission of the assignment written in the assignment is not correct. You're supposed to submit homework number 1 until tonight, and the date written in the exercise is 19th of May, even not in April. So basically it's a mistake. So once again, the submission is open until tonight. Tonight, the submission at the Moodle will be closed and the exercise checker will start to check the exercise because they have to return it until the next week. Okay, I will give you a moment to draw the automaton that accepts all words over alphabet 01 that have even number of ones. How many states should we have?
3 states?
3 states? Why not 2?
2.
I think 2 will be enough. Let's see the automaton. Okay, if I start with Q0, the first question, do we accept an empty word? An empty word doesn't have any letters.
Of course, because it has 0 ones.
Exactly. So Q0 should be an accepting state. And if I get any zeros, I continue to stay in this state. If I get 1, now I have odd number of ones. So I move to Q1 that actually represents a counter of odd number of ones. And I stay here until I get zeros. If I get additional 1, I move to Q0 that represents even number of ones. So basically I have 2 states. Each state is actually a counter of ones in the word. We are not interested in zeros here. So basically I have a solution. I have an automaton that solves my problem. Now I need to give a formal proof. And usually in our course, you are not asked to give the formal proof because it takes time. and usually you don't like so much all the theoretical issue of this course, but here and there we are giving you the solutions, or we are giving you an exercises where the solution should be the formal proof of what you did. So basically what I will do with you now, I will give you the formal proof that the automaton we built and the language we have are the same. To prove that the automaton that we built and the language that we have is the same language, I start with some definition. I defined some function G over W. The G over W gives me the number, the resulting number, that is a reminder of counter of ones in W modulo divided by 2, modulo 2. Now, that's what we told. We have O0 as a counter, or 1. And we have Q0 actually representing that the number of ones is even, and Q1 is representing that the number of ones in word is odd. So now we define some lemma that will help us with our formal proof. We define the following lemma. The function GW equals I, and we have two choices, or 0 or 1, if and only if delta cap extended transition function that we start to read a word for W at the state Q0. So we have once again Q0 and W. We finish reading it at the state QI. So basically it's the same I. So I would like to claim that if in original language we had a word that after dividing the number of ones by 2 we have a 0, then in automaton that I've built we will finish reading the word in the state Q0. And if I have a word with the odd number of ones, then I have a count, it's the division of counter of ones modulo 2 equals to 1. And the meaning is that in my automaton, I will finish reading in the state Q1. Okay, so now we have some lemma that actually is a relation between the automaton we built and the original language we have. So we need to prove this lemma, and I prove only the first direction. You will do the second direction, the backwards, at home during your homework. So I start with my automaton that I've built, and I use extended transition function, delta cap. I start reading in state Q0. I have a word W, and I would like to claim that if I finished reading the word W in state QI, the meaning is that the number of ones in W equals to I. So if I finished in Q0, the number of ones modulo 2 is 0. If I finished reading in Q1, the number of ones in W modulo 2 is 1. Okay, we have 4 possibilities of proof. We have syllogism using modern opponents, doesn't help us here. We have proof by construction. We can't prove that automaton that we constructed is the correct one by construction. We can prove by contradiction, but here it's not the logical one. So we have the fourth choice, proof by induction. And proof by induction is actually what we will do. The induction will be over the length of the word W. So I start with induction basis. I choose an empty word, epsilon, and I claim that the number of ones in empty word 0. And if the number of ones in empty word is 0, then I finished reading the empty word in state Q0, which is an accepting state. And if I use my function GW that I defined, the number of ones in an empty word is 0. 0 modulo 2 is 0. So indeed, we have the GW equals 0. Any questions here about basis? Okay. If not, now we have induction step. I take some word U of the length n, and I claim that U is over alphabet 01 that I use. And I would like to assume that my lemma or my induction is correct for all words until the length n, including this word U with the length n. So I assume that induction is correct, induction step, and my lemma is correct for all words until the length n, including the length n. Now I do an induction step, and I take a word with the length n plus 1. How do I build the word with length n plus 1? I take my prefix u and I add additional letter. So we know that is with length n, and we add some sigma. That sigma can be or 0 or 1, and we have to check the both choices. According to the definition of extended transition function, if we start reading our word W, which has prefix U and suffix sigma, from the state Q0, we have the transition from Q0 over the whole prefix U until we reach some state, let's call it P. And then we have only one transition over the letter sigma. And this transition will end with in one of the states, or Q0 or Q1. So here I actually using the definition of transition function. I don't claim anything. The transition function over the whole word. First of all, I have to check where I get when I read my prefix U. Then I do one additional step. Where do I go with the letter sigma? But we know that the word U of the length n belongs, or according to our hypothesis, when I finished reading the word U, starting with state Q0, I finished in some state Qj in such way that my lemma function G over U also gave me J. So if the number of ones in U was even, I finished reading in Q0, and function G over U with even number of ones also should give me 0. If I finished reading U in the state Q1, that means that I have odd number of ones in U, and that means also that the function G over U should give me 1. Okay, so this one was our assumption, that over each word of the length n, the induction hypothesis is correct. Now I start actual proof, the next step. The next step, I add additional letter, sigma. We have alphabet of 2 letters, so I have only 2 choices, 0 or 1. And I will analyze all the possibilities. The first possibility is that I had a word U with even number of ones. So when I started reading the prefix U from Q0, I finished reading it in Q0. And by induction hypothesis, we know that G of U equals 0. Now I analyze the word W. The word W is built from prefix U and sigma. When I started reading U from the state Q0, we know that I moved to Q0 because it was what we assumed. So now I have to analyze. If I finished reading the prefix U in Q0 and I have additional letter sigma, where should I move? And what is the meaning of my move? So for sigma, once again, I have two possibilities. Or sigma is 0. If the sigma is 0 and the word W have prefix U that finished in state Q0 and the additional letter sigma that is 0, Q0, 0, we know, we see our automaton, Q0, 0 is actually, we're staying at the same state, Q0. Okay, so we know that now when we added additional 0, we didn't change the number of ones in word W. We stayed at 0. And the meaning is that we still have an even number of ones. So let's analyze our function. GW is actually G of the prefix U with additional letter 0. That means, since I didn't add any ones, G U0 is actually G of U, because I'm actually interested only in number of ones in U. And if previously the number of ones in U was 0, so I'm indeed having once again the number of ones in U that is even. And the meaning of my function that represents division of number of ones by 2, modulo 2 equals 0. Okay, we are still here. And we have to analyze the second case. What happens if we finish reading our prefix at the state Q0 and the additional letter we get is 1? If our sigma is 1, then we started reading W at the state Q0. First, we read our prefix, and our prefix lead us to the state Q0. And now we have additional input, which is 1. In our automaton, Q01 moves us to the state Q1. So with additional 1, we moved from Q0 to the state Q1, and we claim that now the number of ones in W is odd. Why? The G of W equals to GU with additional letter 1. Prefix U with additional letter 1. GU had even number of zeros, even number of ones, so GU is 0. We added additional 1, this sigma. 0 plus 1 modulo 2 equals 1. So basically what we have, if our prefix of the length n was with even number of ones, then now when we add in our automaton additional letter, we move to the same state or to the same representation that also function G over the word W will move or will compute. So in automaton, we move or to state Q1 or we state in the state Q0, but the meaning is that also the function G over W or stayed equal to 0 or change to 1.
What question?
Mm-hmm.
here you assume that U is ending in Q0 in this
Yes.
case. You need to do the same for Q1, but it's
Exactly.
the same, right?
Exactly. That is the next slide. I'm doing the same thing once again. Since I don't know what happens with my prefix, now I need to do the second assumption, that what happens if I had a prefix with even number of ones and I finished reading it in Q1. And I assume, induction hypothesis, that G of U equals 1 because we have an even number of ones, an odd number of ones in U. So now once again, we are looking at word W, which was built according to some prefix U with additional letter. We now know that Q0U is 1. So what we have to check is only one transition. Where do we go from the state Q1 in our automaton when we have additional letter? And does it equals to what we have in function G? So once again, I analyze two choices. I have the first choice. The additional letter sigma is 0. So I start reading the word at state Q0, the word W. W is prefix U and additional letter sigma. When I read prefix U, I finished at state Q1. So now I have to check only a single transition from the state Q1 with 0, where do I go? And from the state Q1 with 0, I don't move anywhere. I stay at the state Q1. Why? Because the number of ones is now odd. So let's see that it actually the same happens with the function G. G of W is actually G of U with additional of one letter 0. G of U we know is 1. Additional 0 doesn't change as the number of ones in our input. So we have GU, and we know that GU is 1. So if we finished reading in our automaton at the state Q1, the function G over W also gives us an output 1. Let's check the second case. The second case, I add additional letter sigma 1. So once again, we start reading the word W at the state Q0. The word W have prefix U and the suffix sigma that currently is 1. The prefix U, when we read it, we finished reading at the state Q1. And now we have additional 1. At the state Q1 with additional 1, in our automaton, we know that we move to Q0. Let's see what happens with the function. If we have G over W, we know that W was built from prefix U and suffix now the word the letter sigma, which is 1. So we have a word prefix U concatenation 1. The prefix U GU gives us 1. That was the induction hypothesis. And we have additional number of ones, the sigma that we added. 1 plus 1 modulo 2 equals 0. So actually, if we move to the state 0 in the automaton, we also have 0 in our function GW. Questions? Okay, so the next step, you need to prove the second direction, and it will be your homework. You need to start with function GW equals I, and you need to show that if GW equals 1 or equals 0, you have the same meanings moving to Q0 or moving to Q1 in your automaton. Yesterday, I was asked, do you have to prove this direction by induction also? Definitely. This direction, the second direction, you have to prove also by induction. And the last step, I need to prove why did I do this lemma and why I wanted to prove it? Because of what is written here. I had to prove that the original language and the language of automatons that I built are the same. So let's do this proof. I start with the word W that belongs to the language of the automaton. According to the definition of my automaton, extended transition function delta cap moves on the word W.
A question.
Mhm.
What are you doing to prove? I don't understand what the language.
What I did before, I proved that the lemma and that automaton are actually the same.
Okay.
Now I have to prove that the language that I was given, and the language that I was given is this one, and the automaton LA that I built are the same.
Oh, okay. Thank you.
So I start currently with the word, and I will use this lemma. The lemma was important because I'm using it here in my proof. I start with the word W belonging to the automaton. The meaning that the word belongs to the automaton, if I start reading it in Q0, I finish reading it in Q0. According to the lemma we just proved, the meaning that W is accepted by my automaton, the meaning that W has even number of ones. And according, okay, the meaning is WG equals 0. According to the definition of function G, the number of ones in W is even. Therefore, W belongs to the original language.
Why does the first part work? If a
What-
word is in the first part, the leftmost, the first if and only.
This one?
No, the first left.
The first one? Okay.
If a word is in the language of the automaton, why is that an if and only if that it ends with a
Because
Q0?
you have only one accepting state. The word belongs to the language of the automaton.
Oh.
If after you finish reading it, you are in the accepting state.
Oh, okay.
We had only one accepting state, so the meaning is here only Q0.
If you had more, you had to split two cases?
Yes, definitely. Okay, now I think you have Zoom with Holocaust. So basically, if you want, we can continue, but we finished. It's our last slide for today. Additional things that I wanted to mention, you have additional proof of a little bit different language in Hebrew book of Open University. So if you want to use it, you are welcome to check it also.
A short lecture today?
It's not lecture. Lecture is already recorded. It's only practical exercises. So the practical exercise should take something like 1 hour, a little bit less, a little bit more. So basically we finished. If you want us to continue, if you want, I can leave the meeting open or just.
Two questions.
Wait,
one,
where is the lecture? The second lecture?
in YouTube.
On YouTube.
YouTube in your Moodle.
It's the link is at the Moodle. You have two versions in Hebrew and in English, and you can use it.